Hey guys, hope you did well on your test yesterday. We are going to move on to the next section, and today's and tomorrow's lessons I'm going to incorporate into one recording, and I'll let you know where I normally finish up in terms of where I would pause after the first day. The first part of the lesson today is to talk about and review skills of simplifying radicals. You would have learned this in Algebra 1. You also would have done some practice in geometry on how to work with a radical. So your warm-up today was to simplify the square root of 128. So just to make sure we're all on the same page, I'm going to put that down as an example. We are in the fourth section of the quadratic unit, and the notes that we're going to be talking about in our notebook has a focus of simplifying radicals. Now, this is not the name of the section. The section is on complex numbers, but this is our goal today. That is our objective for the first half of class within section 2.4. So for all of the examples, we're just going to dive right in. The goal is to simplify the radical. When you're simplifying, you want to keep in mind your perfect squares. They're going to come in handy. I'm just going to go ahead and list the first few perfect squares. Okay, so 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, etc. And I'm going to keep going all the way up to 16 times 16, and these are the ones that you guys should become most familiar with. I know it's a lot of them. And 256. Obviously, this list is infinite because you can keep on squaring numbers, so on and on and on and on and on. So with that warm-up example, when you had to simplify the square root of 128, your goal is to find the largest one of those perfect squares that goes in evenly into 128. You usually want to start checking with the larger numbers and work your way down. So 128, obviously, the ones in the 100s aren't going to go into 128 evenly. If I double 81, that's already bigger than 128. I would start probably with a 64, and that is going to work. If I do 128 divided by 64, it goes in 2 times. So we would break this radical apart into the square root of 64 times the square root of 2. I always write the perfect square first. The one that's a perfect square is the value that comes out of the radical because you're actually square rooting it. The square root of 64 is 8. The square root of 2 is a decimal. So 2 is going to stay under the radical. So it's 8 times radical 2. 8 radical 2 is the answer to that question. I'm going to put another one up here. 3 times the square root of 12 times the square root of 6. You could try to break apart the 12 first, but I suggest when there's more than one radical and neither of the radicals are perfect squares already, just to combine them under one radical and then break it apart. So 12 times 6 is going to be 72. From here, we're looking for the largest perfect square that goes into 72. I'm going to give you guys a minute. I'd hit pause, see if you can find that value. And you should have gotten 36. Which goes into 72 2 times. It's not always going to be the number times 2. Just kind of coincidence that both of these turned out that way. This will become 3 times 6 radical 2, which is 18 radical 2. So those are just 2 examples of how to simplify the radical by finding the largest perfect squares. The other 3 examples we're going to put in our notebooks have to do with fractions. So if I gave you the square root of 7 over 16. So a quotient property allows you to break this apart into 2 separate radicals. So square root of 7 divided by square root of 16. You can separate them. By doing that, the 7 is going to stay under the radical. We can't do anything with 7. There's no perfect squares that go into it besides 1. And then the square root of 16 is 4. So we get radical 7 over 4. So it's the quotient property that allows you to break apart a fraction under a radical. And it's the product property that allows you to do the process that we did in example 1 and number 2. These properties only work with multiplication and division. You cannot apply these properties with adding and subtracting. With adding and subtracting, they have to be like terms. For example, you could only add radical 2's to other radical 2's. Those are like terms, just like you can only add x's with other x's. If you wanted to do like radical 2 plus radical 6, which are not like radicals, you would have to change them to their decimal form to be able to do the addition. Next example, if I have the square root of 15 over 2. I'm going to break them apart just like in the last example. And I'll look at the numerator and denominator separately. Square root of 15, I can't do anything with that. There's no perfect square that goes into 15, and there's no perfect square that goes into 2. 2 can't come out of the radical. It's not a perfect square. We cannot leave it like this, though. We're not going to leave any of our answers with a radical in the denominator, so we're going to do a process called rationalizing the denominator. We did one problem at the beginning of the school year when we were doing isolating that involved this skill. So we're going to multiply the numerator and the denominator by whatever that denominator was, so radical 2 in this case. Because the 15 and the 2 are both underneath a radical, you're allowed to multiply them together to get radical 30. Radical 2 times radical 2 is radical 4 in the denominator, and the square root of 4 is just 2. There's two things you should look for or keep in mind here. First thing is, can you break apart radical 30? So is there a perfect square that goes into 30? If you think about that for a minute, then hit pause. And no, there is not. Now the second thing you need to be careful of is the 30 is under the radical, the 2 is not. Therefore, you cannot do 30 divided by 2. Because one is under, one is not under. So you cannot do that division. So that is as far as that example would be able to go. All right, and why don't you guys try this last one, 6 times the square root of 25 thirds. So have you hit pause, try it on your own, and you can check to see if your answer matches with my answer. First thing I'm going to do is break this apart and also put the 6 over 1. Okay, I could rationalize right now, but be on the lookout for perfect squares at all points in time, because 25 is a perfect square. It'll make this problem a little simpler if you take the square root of 25 first before you rationalize versus after. You won't be working with large numbers. So this is going to become 6 over 1 times 5 over radical 3, which I can turn into one fraction at this point. 6 times 5 is 30. And 1 times radical 3 just stays radical 3. You don't need to put the 1 in front of it. I'm going to rationalize. And I can't do 30 divided by 3 because the 3 is under the radical. This will give me 30 times radical 3. Can't do 30 times 3 for the same reason I can't divide. 1's under a radical, 1's not. And this would be over the square root of 9 on the bottom. And the square root of 9 is just 3. Anytime you multiply a radical by itself, essentially the radicals cancel out and you're just left with a number that is underneath, which is called the radicand. I can do the 30 divided by 3 because they both do not have a radical to get a final answer of 10 radical 3. So those are the only examples that we're going to do with the radical problem, with the simplifying radicals. And we will do some later where we apply this same skill but with imaginary numbers. So we're going to learn about the complex number system for the remainder of class. So the complex number system notes are going to be on a handout that you're about to get. So we're going to be working through a note packet. I'm going to pull that up right here. Okay. And talk about the complex number system. So complex numbers encompass real numbers and imaginary numbers. So where do these imaginary numbers come from? Why do they have to exist? So let's look at a quadratic to help explain that idea. So not all quadratics have real solutions. So solutions here are referring to the x values, the x-intercepts, and it gives you an example of a quadratic. So x squared equals -1. That was right here. Okay, this would have no real solution. If I tried to solve that for x, I would square root both sides. And when I tried to square root the -1, if I did it on the calculator, it would say error. And if you tried doing it in your head, you'd probably get an answer that you think is right but is wrong. So there's no solution to this. If you think back to our unit on domain restrictions, square root functions, all even root functions, had a domain restriction because you couldn't take the square root of a negative number. Because anytime you square a negative, it comes out positive. There's no way to get a negative answer. So there's no real solution, because we can't square root that negative. However, there is an imaginary solution. So graphically, if we were to make a graph of a quadratic that had no real solutions, it would not ever be able to touch the x-axis. So it would either need to shift up and open up, or shift down and open down. So that relationship that we learned earlier this year between the a value and the y of the vertex, so they would need to be the same sign in order for it to never touch the x-axis and produce no real solutions. It does have imaginary zeros, imaginary solutions as part of the complex number system. So to overcome this issue of not being able to square root a negative, there's this expanded system of numbers that use the imaginary number I. This is the definition of I. Okay, I'm going to have you guys put a box around that. By definition, I is equal to the square root of -1. So if you look back up at the answer that I said had no real solution, if I square root -1, by definition, what is the square root of -1? Yes, it is I. So it would be technically x equals plus or minus 1i. You still need that plus or minus sign anytime you square root both sides of an equation. It'll give you 2. So we would have 2 imaginary answers there. The idea of solving is going to come up more next section. This section is more just practice doing operations and simplifying with imaginary numbers. So let's try some more simplifying radicals, like the ones we just did in our notebook, except with negative radicals. So I'll do one with you, and I'm going to have you guys try the other one. So the square root of -9, technically you could break that into the square root of 9 times the square root of -1. You don't have to do this every single time. I just want to show you where the answer is coming from. So the square root of 9 we know is 3, and by definition the square root of -1 is I. So our answer, when we simplify and break apart that radical, is 3i. You do not need the plus or minus sign because we didn't do any inverse operations in trying to isolate. We're just simplifying at this point. So we have 3i. What I expect you guys to do is just recognize that anytime there's a negative under the radical, it's going to come out as an I. It means our answer is imaginary. So square root of 9 is 3. The negative under there means I. So I'm going to have pause the video. You guys try the other ones all on your own, and then you can check to see if you got the same thing as I did. 16, perfect square. Square root of 16 is 4. The negative comes out as I. 27 is not a perfect square. I'm going to break this apart into radical 9 times radical 3, and the negative still comes out as I. The square root of 9 is 3. And this is the correct order you write it in. And you might not have done this because it's the first time we're ever doing it. The square root of 9 is 3. The whole 3 comes first. The I is going to be squeezed in the middle, and the radical is going to come last. That is the typical order you will see it. The coefficient, the imaginary I, and then the radical. So 3i radical 3. The next one is going to be broken into square root of 49 times the square root of 5 times I, which will be 7i radical 5. And the last one, square root of 5 can't be broken apart, so 5 must stay under the radical. The only thing you can do here is pull out the negative as an I. So it's I radical 5. All right, so we're going to use another property about I with the examples down below. This is about to be erased, so I can scroll down. And that's the definition, or using the definition of I to come up with another fact. So if we take the definition, which is I equals the square root of -1, and we square both sides, let's see what we get. So if I take I equals the square root of -1, and I square the left, and I square the right. So on the left, I now have I squared. On the right, squaring and square rooting are opposite operations, so they cancel each other out, and you're just left with -1. So this is another property that will become used throughout this section. This is a very quick 2-day section. So I squared is equal to -1. And we're going to use that definition to fill out the box below, which helps you find some patterns of I. So powers of I. This is I to the first power. I to the first power is just I. We just learned that when you square I, it results in -1. Now the other two boxes, we're going to use a combination of these two to figure out what they equal. So I could technically rewrite I cubed as I squared times another I, because I squared times I is I cubed. We know that I squared is -1, and I is I, so -1 times I is -I. So I cubed is equal to -I. I to the fourth, I could either write as I cubed times I, or I could also write it as I squared times another I squared. And I squared is -1 times another -1, which is +1. So I to the fourth power is +1. I could keep working through this same process. So I to the fifth, I could write as I to the fourth times I, which would be 1 times I, which is still I. And then I could keep going through that whole process, but I'm just going to tell you what the rest of the box is going to fill into to save a little bit of time. So I to the sixth is going to end up being -1. I to the seventh will be -I, +1, +I, -1, -I, +1. So do you guys see any patterns occurring? I'm going to pause, look for patterns in the table, and describe anything you see. Okay. You guys should notice that every 4, it repeats itself. So I, -1, -I1. I, -1, -I1. So that pattern will just repeat itself over and over and over and over again. Therefore, we could use that pattern to do questions like I to the 99th power without going through and filling out 99 boxes. The easiest way I think of doing it is, since the pattern repeats every 4, is to divide 99 by 4 and see how many times 4 goes into 99 and multiply it by that value. So what I mean by that is I'm going to rewrite this as I to the 96, because 96 is the highest multiple, largest multiple of 4 that goes into 99, but there's still a difference of 3 i's missing, so I'm going to multiply that by I cubed. Since this value right here is a multiple of 4, I'm going to be using this column. So I to the 96th power is 1 times I cubed, which we know in our table is -I. So we will end up getting -I for an answer. Okay. You could have also just realized that 99 itself is a multiple of 3. Therefore, it's going to come in to that category and just get -1. So it's up to you as to whether you want to use the fourth power or figure out what it's a multiple of. There's a couple different ways you can do it. Okay. We still have a lot more to learn about these imaginary complex numbers. So flip the page and we'll keep taking some notes. Okay, so this is the definition of the imaginary number, which is part of our complex number system, and this chart, I think, gives a good visual. So an imaginary number in standard form, this is different than standard form of a quadratic, so we're not using ax squared plus bx plus c here, is of the form a plus bi, where the a and the b are real numbers, and a is the real part of it, and bi is the imaginary part. So a plus bi is a complex number. The a is the real part, and the bi is the imaginary part. And b can't equal 0, or if b is not 0, then it's purely it's an imaginary number. And if a equals 0 and b is not 0, then it's a pure imaginary. So slight difference between imaginary versus pure imaginary. It's just asking you, is there an a value or not? So if there is an a value, it's still an imaginary. And if there's not an a value, it's pure imaginary. And we're going to look at the Venn diagram to show this relationship. So complex numbers is the whole number system. It includes everything, real and imaginary. So we have the real numbers and the imaginary numbers. So real numbers are numbers that we're used to working with, like -5, 7, 1/2, the square root of 8. Okay, those are all real numbers. I could throw a decimal on that list if I wanted to. Imaginary numbers are going to come into this form, the a plus bi, so like 2 plus 5i. That's an imaginary number. It has an imaginary component to it. A pure imaginary number would be just the 5i, so it would have an a value of 0. Now, real number system is also broken into different components. Within real numbers, there's rational numbers. Those are numbers that can be written as a ratio or a fraction. Whole numbers are rational. I can put like the number 9. Repeating decimals are rational, like 2/3. Anything that could be written in fraction form is a rational number. 1/4. It can be positive or negative. I'll make that one negative there. Even in decimal form, it's still rational. Like 0.2 is a rational number because you could rewrite 0.2 as 1/5. Integers are the numbers that you're more familiar with on the number line. So those are positive, negative, and 0 whole numbers. Okay, so you're looking at numbers on the number line. Basically, no fractions, no decimals. No fractions, no decimals. Whole numbers include 0 and above integers. So you're basically saying non-negative integers. So 0, 1, 2, 3, 4, etc. Still no fractions or decimals because they are integers. And then irrational is all on its own there. Irrational are numbers that can't be written as a ratio or as a fraction. Pi is an irrational number. The square root of 2 is an irrational number. So when you take the square root of 2 and get that decimal, there's no way to write that decimal in its fraction form unless you're rounding it. Those are just some examples of irrational numbers. So the rest of the notes are going to be performing operations with the imaginaries. My goal for day 1 is to get just through the addition and subtraction, and then tomorrow we will focus on the multiplication and division. So a little more notes for today if we're on track, which is the adding and the subtracting. So we're going to write them as a complex number in standard form. So our goal is to get it in the a plus bi format. And really just think of I like a variable, and it's combining like terms. So you're going to combine real parts and imaginary parts when you're adding and subtracting. So for addition, you could literally just drop the parentheses. that are around each complex number, and then combine like terms. So 4 plus 3 is 7, and negative 1i plus 2i is positive 1i. So we get 7 plus I. What's the trick with subtraction? I'm going to pause here, let you guys think about that and share the answer. Subtraction, you do have to distribute the negative 1. Please pay attention that there are symbols in between these imaginary numbers. We have a plus sign, we have a minus sign. That is really important because a lot of times students just rush through these and think this is multiplication. This is not multiplication, so watch your operation. First one is going to stay 7 minus 5i, and if we distribute the negative 1 into the second complex number, we will get negative 1 plus 5i. When we combine like terms, 7 minus 1 is 6, and the 5i's cancel each other out. So when we subtracted those imaginary numbers, we got a real number. And the last one for adding and subtracting has a couple steps to it. We're going to start off by distributing not the 6, but the negative 1 here. So negative 1 times negative 2 is positive 2. Negative 1 times 9i is negative 9i. For the second one, we're distributing a positive 1, which won't change anything. When you add a negative 8, adding a negative is just subtracting. So instead of doing plus or minus, I'm just going to write a subtraction sign, and then it'll say plus 4i. Combine all of our real parts. So 6 plus 2 is 8, and then we have a minus 8, so here the real parts are going to end up canceling each other out, and negative 9i plus 4i is negative 5i. So we end up with a pure imaginary. So the first one was imaginary, second one was real, and the third one was pure imaginary. So this is where I would stop on day 1. The homework is not really homework until tomorrow night, but it's part of this packet. You'll see there are some SAT questions. Nothing is due tomorrow, but I would encourage you to do as many that you can tonight so that we have less homework tomorrow night. And then tomorrow we're going to focus on multiplying and dividing. So I'm not going to stop the recording here. You would be done for the day, but I'm going to continue on in this packet and now do day 2's notes on multiplication and division. Okay, still really no new skills. So let's go ahead and for multiplication, we're just distributing. The one thing that's going to be challenging is that, keep in mind, our answers need to be in A plus BI form. And you'll see something happen here when we get our first answer. So I'm going to go ahead and distribute the 5i. So I'm going to get negative 10i plus 5i squared. There is no I squared in standard form. But I did learn a fact yesterday, and that is I squared equals negative 1. So I can replace the I squared with negative 1. So I squared should not be in your final answer. Keep in mind real part, then imaginary. So when I do 5 times negative 1 and get negative 5, that should be written first, and then the minus 10i. So it's in the A plus BI format. Second one, we're going to distribute all the way out. So 7 times negative 1 is negative 7. 7 times 2i is positive 14i. And we're going to get positive 4i. And negative 8i squared. We can combine the like terms and replace I squared with negative 1. It's going to be negative 7 plus 18i minus 8 times negative 1. So negative 7 plus 18i plus 8. And if we combine like terms, we will get 1 plus 18i. The last one, before you guys try the multiplication on your own, I would like to write a vocabulary word next to this. These expressions are called conjugates, because if you look at them, it kind of reminds, or it should follow the same format of like a difference of two squares. The factors, or the imaginary numbers, are identical except for their signs. That's called a conjugate, when one's addition and one is subtraction, but everything else is the same. So hit pause, try this on your own, and check with my answer. I distribute, I'll get 36 minus 18i plus 18i minus 9i squared. If you multiply a conjugate or a number by its conjugate every single time, these middle terms will cancel out. So if you wanted to save some time, you really only need to multiply the first and the last terms, because the middle terms will always cancel when you multiply by its conjugate. We're going to get 36 minus 9 times negative 1. 36 plus 9 gives us a real answer of 45. And the last skill for today's notes, and then you will have some time to work on homework in class today, is division. And you'll notice down here it gives you an example. I'm kind of getting ahead of myself. Gives you an example of a conjugate. So two factors, a plus bi, a minus bi, and the answer will always be a real number. And we're going to use the idea of conjugates when it comes to division. So you guys could write your own example if you wanted to of multiplying a complex number by its conjugate. So hit pause, try one on your own. This will be mine. 2 plus 8i, 2 minus 8i. And if I multiply my example, remember the middle terms will cancel. So I really will just get 4 minus 64i squared. I squared is negative 1 times negative 64. So this will become 4 plus 64. My answer would be 68. Real answer, real number. So now let's move on to the division. Sorry, I was getting ahead of myself there earlier. So just like with radicals, and we're now have a radical in the denominator, we don't really want any complex imaginary numbers in the denominator either. So to get rid of the imaginary numbers in the denominator, we multiply top and bottom by the conjugate. So in example number 1, the conjugate of 1 minus 2i would be 1 plus 2i. So I'm going to do that to the top and the bottom, because I know that when I multiply an imaginary number by its conjugate, I get a real answer. I will no longer have an I in the denominator. I'm also going to throw parentheses around these to show that I'm multiplying. When I distribute out the numerator, I will get 5 plus 10i plus 3i plus 6i squared. And since the denominators are conjugates, I'm not going to distribute it all the way out. Okay, I'm going to use the strategy and the shortcut and only multiply the first and the last. So 1 times 1 is 1, and negative 2i times positive 2i is negative 4i squared. Could multiply it all the way out if you forget. They'll still cancel. From here in the numerator, I'm going to get 5 plus 13i plus 6 times negative 1 over 1 minus 4 times negative 1. In the top, 6 times negative 1 is just really negative 6, which I would combine with the 5. And 5 minus 6 is negative 1 plus 13i. Over in the bottom, negative 4 times negative 1 is positive 4. And 1 plus 4 is 5. We're not going to leave it like this because in the standard form it's a plus bi. They're separate terms. So I'm just going to divide them individually by 5. So my final answer is negative 1/5 plus 13/5 I. So I'm just dividing them by 5 separately. Just double check to see if you can simplify either of those fractions, but in this case you can't. I'm going to have you guys hit pause and see if you can try the second one on your own, and then check with my answer before starting the homework. I'm just going to hit pause real quick on my screen because the bell's about to ring and I don't want the bell to interrupt. So I'll be back in. All right, if we finish off this last example, just like before, we're going to multiply by the conjugate. Bell just rang, so it's a little loud in the hallway if you guys can hear that. Multiply everything in the numerator and denominator. So we're going to get 12 minus 18i plus 8i minus 12i squared over the conjugates will give me 16 minus 36i squared. Middles will cancel out. In the top, I'm going to skip a couple steps here as we're getting more comfortable, or should be getting more comfortable with the fact that I squared is -1. So negative 12 times -1, this is going to become positive 12, which I can combine with the other positive 12 to get 24, and then minus 10i when you combine the i's. In the denominator, we're going to get negative 36 times -1, which is really positive 36, which we can add with the 16 to get 52. I'm going to separate them out. 24 over 52 minus 10 over 52i. If I divide those fractions individually to simplify, I could divide the first both by 4 to get 6 over 13, minus if I divide both of those by 2, I will get 5 over 26i. And that is the final answer in standard form. So the rest of class, you guys get to work on your homework and practice these skills of radicals and adding and subtracting and multiplying and dividing with the imaginary numbers. And then the next day, new section. Bye, guys.